Good afternoon. My name is Kate Kreiderman, and I'm here today with Ariel Pavlick, who will also be co-presenting with me. We're going to be talking about the Resource Prospector mission, or RPM, and more specifically, the Resolve science payload that will fly on this mission. I work on the lava subsystem that we will talk about, and Ariel works on the avionics subsystem. And I also just want to mention that the Resolve science payload is a collaboration across NASA, at KSC, JSC, Ames Research Center, JPL, and also the Canadian Space Agency and Glenn Research Center as well. So let's start talking about our evolving understanding of the moon and its resources. I'm sure many of you are highly familiar with all of this, but back in the 1960s, there was a theory that water was trapped in these cold spots on the moon. However, lunar soil samples from the Apollo missions in the 1970s pointed to a dry moon. We didn't find any water in those samples. Later on in the 1990s and then into the 2000s, Clementine Lunar Prospector and Chandrayaan-1 further suggested that there was evidence in these permanently shadowed regions, or PSRs, on the moon. And then finally, in 2009, LCROSS impacted the moon and used instruments on board to analyze the plume cloud and found water at this specific location. So now, what's the next? With the LCROSS data, we now know that with certainty that there is water at one location on the moon. What we are unsure about is the distribution. So we are seeking to understand if the water there is a usable resource. And in order to understand this, we need to understand the distribution and the accessibility. If it's not accessible, then we can't go on to do further in situ resource utilization. So Resolve is the ground truthing mission that will return to the surface of the moon on this Resource Prospector mission. So Resource Prospector mission, it's going to be short duration, 7 to 10 days. It's a Class D mission, so it's capped at $250 million, including the rocket. We'll be going to the surface of the moon to look at the surface as well as the subsurface to analyze the volatiles there. And we'll also be demonstrating ISRU via hydrogen reduction, or what we call regolith oxygen extraction. So this is just a demonstration. Further missions, 5, 10, 15 years down the road, we'll be looking to scale this up and mine more soil and take this to larger scales. There's a photo at the bottom of the screen here that's our field demonstration unit that was actually tested in Hawaii back in 2012. So our rover, or the payload itself, is constrained to about 105 kilograms or 220 pounds. And we're working within a 300-watt steady-state budget. And the payload itself will be responsible for the heat rejection of the science payload. So here's a look at the flight design for the Resolve science payload. You can see the solar panels. Let's see if I can work the laser pointer. You can see these 2 vertical solar panels here that will be responsible for charging up our batteries. Because we're short duration, ideally we'll be located just outside of a permanently shadowed region so we can rove in and then out to recharge our batteries. On the right is a more specific detailed view of the way the instruments are actually packaged on the payload. So what you see here is actually this greenish brownish box. The tall instrument is our sample acquisition and transfer system, or our drill that then transfers the soil to our furnace. So our Resolve mission requirements can really be broken down into a primary and a secondary mission. The first is to look for water on the moon. That is our primary focus. We'll be using our drill to go down about 1 meter into the soil and then heating this up and analyzing the relative abundances of water in addition to CO2, methane, sulfur dioxide, and so on. And these are derived from data that came from LCROSS. Our secondary mission that I mentioned is hydrogen reduction. So we'll be taking hydrogen with us to prove that we can create water, and then future missions will electrolyze this water into hydrogen and oxygen for life support and propellant. So the evolution of Resolve. Resolve began about 9 years ago in 2005. In 2008, we conducted our first analog mission in Hawaii. You can see it's a pretty small picture here, but we actually had a second rover just for the avionics. So it was large at the time. In 2010, we conducted our second analog mission, and then another in 2012. This is the last we've done. Since then, we're only using 1 rover, and progressively the analog missions have the hardware has become progressively more flight-like. Last year in 2013, our Flight Project Office was set up at Ames Research Center. And then this year we've been working on our risk reduction phase, targeting those highest risk parts of our design so that as we move toward our flight design, we can reduce the risk as much as possible. So we're actually in the midst of conducting testing in our thermal vacuum chambers so that we're actually simulating the environment that we will see on the moon. And then we'll be working on our flight development in 2015 to 18, followed by a launch to the moon in 2019. So this is a photo of our field development hardware in Hawaii in 2012. It was on Mauna Kea, a volcano in Hawaii. This was a collaboration with the Canadian Space Agency. You can actually see our lander here, and then the science payload mounted on the rover. The photo itself actually looks like it could have been taken on the moon, which is kind of a cool image. One other highlight I wanted to point out in this image is that key success was our ability to teleoperate, remotely operate all our hardware from Canada, Kennedy, Florida, and Johnson Space Center as well. So real quickly, let's go over the concept of operations, how we plan to operate this hardware. So prepare yourself for acronym overload. Try to spell it all out. So when we land at one of the lunar poles, we will begin roving around. We'll use our neutron spectrometer subsystem, which is mounted on the front here, to look for hydrogen hotspots in the soil indicative of water. We'll also be able to use our near-infrared volatile spectrometer system, or NIRVIS, to look at the actual drill site as we're roving. So we have these two instruments, the NSS and the NIRVIS, that will provide us real-time data on the constituents on the surface and subsurface. From here, we'll use our sample acquisition and transfer system, which is essentially the drill, to drill down and then pick up a core of soil that's broken into 4 segments. We'll then transfer this into our oxygen and volatile extraction node, which is basically a furnace. We'll typically operate 150 degrees Celsius, and this is the magic number to prevent condensation within our subsystem. So the oven in the lava subsystem will be heated to 150. And then lastly, we will transfer the hot gases that are evolved in the oven subsystem over to the Lunar Advanced Volatiles Analysis subsystem to use our instruments on board to actually characterize the components in the sample. And one other interesting fact to point out is that there are multiple combinations of instruments on board that, if others were to fail, would still result in mission success. So for example, if lava and oven were to fail, NIRVIS and NSS would still meet the mission success. Now I'm going to pass it over to Ariel. She's going to dive a little bit deeper into the functions of the subsystems.
So now we're going to talk more about the subsystems themselves. So the neutron spectrometer subsystem, known as the NSS, looks for these hydrogen hotspots. And we'll actually go over, the pictures here are important, but we'll get to that in just a minute. The NIRVIS, the near-infrared volatile spectrometer subsystem, also looks at the regolith and looks particularly at the drill site. It's looking at it while we're roving and then also when we stop and start drilling so that we can see real time when these materials are coming up to the surface, what they're composed of. The drill has the ability, the SAT, the sample acquisition and transfer system, has the ability, sorry about that green color, has the ability to drill down just 50 centimeters or a meter, and we can take the full core. And then delivers that regolith to the oven. Here's the avionics. This is the part near and dear to my heart. It's composed of 2 flight computers, the Proton and the Q6, and then the avionics stack, which does closed-loop control of the rest of the instruments, lava and oven. Here's the oven, which accepts the regolith that's brought up from the drill, heats it up, evolves some volatiles, and then sends it over to lava, which is huge, and Kate will talk about. It's huge. It does a whole bunch. Let's just leave it at that until she starts talking about it. And here's all the subsystems as they're packaged on the rover. You can see the NSS, the screen is a little small. You can see how it kind of hangs off the front there, and all of you see the boxes at the top of the avionics. There's actually a plate there, a cold plate, to help with heat that is not shown. Subsystem status, the lander and the rover and SATs are in work with international partners, or different partners. NSS and NIRVIS are nearly complete. They're both out of Ames, and they have some history. Oven and lava, we are in the middle of testing for ETU. Here's a closer look at the avionics. So as I mentioned, over in the lower right, you can see the gold box is a Proton from Space Micro. The Q6 is a Canadian box from Xiphos. The Proton is our high-power flight computer that runs Linux. I mean, it does everything. We have a database on there. It's like you could play Tetris. The Q6 is small, low-power, redundant. If everything goes to heck, this little guy we hope will keep us going. The avionics stack here, this is an FDU version. For flight, it'll be flipped over on its side. We're going to use the long axis for our connectors. And then here's a representative board for ETU testing. This is just on FR4 right now, not polyaminide. But this is a key point, is we're using a lot of COTS technology on our boards. We're trying to use, best commercial practice and industrial and automotive rated components for most of our boards to try and help keep the cost down. There is one board that we are doing polyaminide, full rad hard space flight, and this is part of that, what Kate referred to. We have sort of a critical path so that we have several combinations of instruments to achieve mission success. Oh, avionics is not the lander or the rocket. Back to Kate.
Okay, so we wanted to give you a little bit more detail on the lava subsystem. So this is kind of the workhorse of the subsystems. We have a gas chromatograph over here and a mass spectrometer. These are modified COTS. We're working with 2 commercial vendors on these. And then we also have an integrated manifold down here with our valves, our temperature sensors, so on. We have a water droplet demonstration. We'll be using that to condense water vapor out of the gas stream and then take an image of it. This will be the first time we'll actually take an image of water on another planetary body, which is pretty exciting. We have 2 operational flows for lava. One's volatile analysis, where we're looking for water, and the second is regolith oxygen extraction, where we are creating water. So this is a quick look at that. Sorry, I can't elaborate. And then right now we're conducting ETU testing in our vacuum chamber. This is what that looks like right now. All the lava components are on this stack with the oven reactors side by side. So we're validating our timeline, our avionics, our software. We really need a good understanding of our timeline since we're constrained to a short time frame, about 10 days. So we'll be working around the clock. As we work toward flight, we'll be using all this data that we're gaining in our vacuum chamber testing to work into our flight design, which is our next iteration. We're working on solidifying our international partnerships for the lander and the rover, focusing on our thermal mass and power budget. We are launching to the moon in 2019. We're pretty excited about this. It'll be the first time America reestablishes its presence on the moon since the Apollo era.